Guys, welcome to the stream. Um, I'm just basically gonna speedrun AP Calc BC1 stream. I have like a notepad to take notes on. That's what I'm gonna use, and then I'm gonna use the ultimate review packet. But other than that, I'll just do the Pomodoro technique, where I'll like study for like an hour, or do it for an hour, and then like take a 5 minute break. The time is running, but I'm about to restart it. But um, other than that, yeah, gonna start now.
The main concepts from calculus are number one, the derivative, which will cover in units 2 through 5, and then number two, the integral, which will cover in units 6 through 8. But both the derivative and the integral are only possible because of the limit, which is why this unit is so foundational for the rest of the course. And even though there are more topics here than in any other unit, there really aren't that many different concepts. I like to think about breaking unit 1 down into 4 main ideas: the idea of the limit and different ways to represent it and estimate it, methods for solving limits, continuity and discontinuity, and then the animated value theorem. So the foundational idea behind limits is that we're moving from an average rate of change to an instantaneous rate of change. And remember that when we're calculating average rate of change, we're just taking the difference in y divided by the difference in x, or delta y over delta x. And that's really easy to see if we look at the graph of a function. So let's say we have this particular graph, and let's maybe say we have 2 points, we pick 2 points. Let's call one of them the point 2, 3 right here. So say this is 2, 3. And then let's also pick, let's say this point right here is 7, 2. So we have 2 points, and the idea is that if we want to figure out how much the function changes between these 2 points, we can use this average rate of change formula. So the change in y, we'll just find the difference between the y values, so we'll say 2 minus 3, 2 minus 3. And then the change in x, we'll take the difference between x values, so we'll say 7 minus 2. And remember that it doesn't matter the order of the points that we use, as long as we stay consistent. So we started with the values in this point and subtracted the values in this point. We could have done it the other way as well, and ended up with the same value. So what we get here is negative 1 divided by 5, or we can call that negative 1/5. So the average rate of change between those 2 points is negative 1/5. So what that tells us here is that when we move 5 units to the right along the x-axis here, and we're doing the 5 from here, when we move 5 units to the right horizontally, we're going to move negative 1 units vertically, or we're going to move 1 unit down. So we move 1 unit down like this. It just gives us slope. And that makes sense if we see that if we connect these 2 points with a line, that line there, we move 1 unit down and move 5 units over. So the slope is negative 1/5, the average rate of change is negative 1/5, and that's over this particular interval between the points 2, 3, and 7, 2. What limits allow us to do is narrow this interval. So instead of using this interval here of 5 units, we get to narrow this interval so that it becomes smaller and smaller, like this, and then smaller and smaller, until eventually we have this tiny little interval, and we're finding rate of change over that tiny little interval. But as long as we have some kind of interval, we're using the difference quotient formula. It's the same as this delta x over delta y, but we often write it as f of x minus f of a divided by x minus a, and we use this formula when we call this point over here x and this point a, or we can use the formula f of x plus h minus f of x all divided by h, and we use that formula when we call the distance here, the interval distance, horizontal distance, h. Both of these are going to give us average rate of change. Of course, this formula is going to work for any interval, no matter how wide or how narrow it is, as long as the interval doesn't eventually go to 0, as long as we don't bring the points completely on top of each other. The reason we can't have 0 is because if we brought the interval narrower and narrower until eventually it had no width, then delta x, the change in x, would be 0. And as you know, in math, we can't divide by 0, so we can't have a delta x that's equal to 0. But as long as we can't have that, that prevents us from finding the instantaneous rate of change at one particular point. If I want to find the slope of the function at this exact point, instead of having an interval around the point, but right exactly at that point where there's no change in x at all, the only way I can do that is with a limit. And in order to get that instantaneous rate of change, I simply apply a limit either to this difference quotient formula, where I say the limit as x goes to a, or to this difference quotient formula, where I say the limit as h approaches 0. If I add this limit notation to the difference quotient formulas, that allows me to narrow the interval all the way to almost 0, but not quite 0, and therefore find an instantaneous rate of change. In other words, if we want to find average rate of change, we use these formulas without the limits. If we want to find instantaneous rate of change, we apply the limits to those difference quotient formulas. And remember also that we'll often be asked to estimate the average rate of change based on a table of values, and the way that we do that is just by plugging those values into the function. We might be given this table and asked, let's say, to estimate average rate of change at, let's say, x equals 8. Well, we don't have x equals 8 in the table here, but we do have 7 and 9. So we'll just go ahead and use the points on either side of 8. We want to get as close to it as possible and plug into the difference quotient formula. So we'll use this first difference quotient formula here again without the limit because we're looking for average rate of change. And we'll call this column x and we'll call this column a. And so then if we do that, f of x is going to be 1, f of a is going to be 6, and then x minus a is going to be 7 minus 9. And so the value we get there is going to be negative 5 divided by negative 2, or we'll get 5 halves. So the average rate of change at x equals 8 we can estimate as 5 halves from the values in the table. In topic 1.2, we really want to make sure that we understand limit notation. So let's go ahead, for example, and write a limit. Let's say the limit as x approaches 2 of a function f of x is equal to 4. We just want to be able to read this limit notation. We need to be able to read it as the limit as x approaches 2 of the function f of x is equal to 4. And we need to understand what this is telling us. All this means is that if we sketch f of x in the xy coordinate plane, and we don't know necessarily that this is what f of x looks like, let's just say that this is the curve f of x. What this limit notation is telling us is that this function f of x, whatever it looks like, that as I come closer into x equals 2, the value of the function is going to come closer into 4. So if I look at the curve here, and I come to 2, I come up here, it looks like I'm about at this point right here. Let's say this is the point along the function, 2, 4. Well, what I'm saying is that as I travel in toward x equals 2, realize here that we have this line along x equals 2, or through this point here, x equals 2. So along this line, as I come close into this line, so as I'm coming here from the left this way, or as I'm coming here from the right this way, and along the function, that looks like this. So we're coming in along the curve like this, we're approaching this point, we're getting close to 2, or from the right-hand side, we're coming in along the function, getting close in toward x equals 2. So as I get close to this x equals 2 line from either side, this limit notation, this limit statement, is specifically saying that I'm coming closer and closer to this value 4. So either from the top or from the bottom, I'm coming closer to 4. And specifically, the limit statement is saying that the closer I get to x equals 2, the closer the function's value will get to y equals 4. So this x approaches 2 notation here under the limit means as we push in horizontally from either side, the function pushes in vertically toward this particular value. That's what that limit notation is saying. That's what we really want to be able to take away from this limit statement. Now we're going to start looking at other ways to estimate limits. In 1.3, we need to understand that we can estimate limits from graphs. In 1.4, we'll talk about estimating limits from tables. But for now, let's pretend that we have this graph. What we really want to remember here is that at every point along the graph, we can think about a left-hand limit, a right-hand limit, and a general limit. So there's 3 different pieces of the limit. Remember, we have this idea of one-sided limits, where we can have the left-hand limit and the right-hand limit be different. In order for the general limit to exist, we need to have the left-hand limit exist, we need to have the right-hand limit exist, and we need the left-hand limit to be equal to the right-hand limit. If these 3 conditions are met, then the general limit exists, and it's equal to the same value that the left and right-hand limits take on. If the left and right-hand limits are not equal to each other, or if one or both of them does not exist, then the general limit will not exist. Only when all 3 of these conditions are met do we have that general limit. So we could look at different points along the graph here and give values or say whether or not the limits exist. For example here, at x equals 3, the left-hand limit, which is the limit as we're coming in from the left-hand side, so we're tracing the graph, we're coming here, we're approaching x equals 3, we can see that value is about 1.5, so the left-hand limit is 1.5. The right-hand limit, on the other hand, as we're tracing from the right, coming in along the graph toward this value x equals 3, we see that the graph has a value of about 1, so the right-hand limit would be equal to 1. Because these 2 values aren't equal to one another, we would say that the general limit BNE does not exist. Similarly here at x equals 4, we would say that the left-hand limit looks like it's about at 2, because as we trace the graph from the left-hand side, we're approaching 2. The right-hand limit looks like we're approaching maybe about 1.25, and because these values aren't equal, the general limit here at x equals 4 does not exist. At x equals 5, we have a vertical asymptote, so we have an infinite discontinuity or discontinuity at the vertical asymptote. The left-hand limit, technically when we have an infinite limit, we say that the limit does not exist or that there's no limit, because a limit of positive or negative infinity is not a real number, and in order for a limit to exist, it needs to be a real number. However, we still will also describe the limit as positive or negative infinity to give information about how the graph is behaving. So we can see that as we approach x equals 5 here from the left-hand side, so we're moving this way from the graph tracing along, we can see we're headed up toward positive infinity. So we would say the left-hand limit is positive infinity. The right-hand limit, as we're tracing the graph, headed here toward x equals 5 from the right-hand side, we're headed off toward negative infinity. And because these 2 are unequal, the general limit does not exist. Here at x equals 7, we have a cusp or a corner of the graph, but that doesn't affect the left and right-hand limits because we can see as we trace from the left, we'll say that it looks like we're approaching about 1.25, and as we trace from the right, we're approaching the same value, 1.25. It doesn't matter that there's a sharp corner here where we change direction. We're approaching the same value from both sides, so the one-sided limits exist, and because they are equal to one another, the general limit there is 1.25. The same kind of thing happens at a smooth point on the graph. So here at x equals 6, for example, if we come up to here, that looks like we're at about 1.5. Well, coming from the left, we approach 1.5. Coming from the right, we approach 1.5. And therefore, the general limit is also 1.5 because those 2 are equal to each other. That would be the same thing here at x equals 2. That's a normal point along the graph with nothing going on. So the left and right-hand limits are going to exist, and the general limit is going to be equal to the left and right-hand limit. Here at x equals 1, I've done my best to draw an oscillating function because when you have a function that's oscillating violently back and forth like this, which you sometimes have with trig functions around x equals 0, but when the function is moving back and forth like this so quickly, it's not ever approaching a constant value. It's not like here at x equals 6 where you're just coming and calling from the left-hand side and the right-hand side and approaching a value where the function sort of stays here at rest and holds this value of 1.5. When the function is oscillating, it's not approaching a stable value like that. And you have to be careful with these oscillating functions because sometimes if you're using a graphing calculator, they don't always show up depending on how you're zoomed in on your graph. So you have to be aware of oscillating functions, and when that happens, we say that at that point, the left-hand limit does not exist, the right-hand limit does not exist, and therefore, of course, the general limit will also not exist. So when you're doing graphs like these on the AP test, you just want to be real careful about each point. Think about the left-hand limit, the right-hand limit, and those values together to determine whether or not a limit exists at a particular point on the graph. The only takeaway we need to get from 1.4 is that we can estimate limits using tables. So for instance, if we're given a table like this, and the question we're asked is find the limit or estimate the limit as x approaches 1 of the function f of x. So this is our question here. All we need to do is look at the table and recognize that we've been given a set of values here for x, 0.7, 0.8, 0.9, 1, and then 1.1, 1.2, 1.3. So we're increasing here by 0.1 each time. And then we have the associated values of f of x, what the function is doing at each of these values of x. And we can see that as we get closer to 1 on the left-hand side, right, this is to the left of 1.7, 0.8, 0.9, leads up to 1 on the left-hand side in an xy coordinate plane. As we approach from the left, the values of the function are getting smaller and smaller. 7.1 goes down to 7.01 and 7.001. The values are getting smaller and they look like they're approaching 7. We want to check on the right as well. The same thing over here, when we're approaching from the right-hand side, and our values of x are decreasing from 1.3, 1.2, 1.1. The values of the function are increasing from 6.9 to then 6.99 to 6.999, and we're approaching 7 from that side as well. So our unknown value, this one here that we're looking for, we can clearly see has to be 7. And therefore, the limit here has to be 7. And we estimate that limit from the table. Just be careful here when you're given a table. Make sure that you understand the values for x aren't always going to be given in ascending order. Here they were. 0.7 is the smallest value on the left, all the way up to 1.3 on the right, the largest value. Sometimes those are going to be flipped, and we may have started with 1.3 on the left and decreased all the way here to 0.7. And then the values of f of x, they may be increasing, they may be decreasing. So just be aware of what's happening to both x and f of x. But you should be able to discern from a table like this one where it looks like the function is going in that unknown spot. Topic 1.5 is about limit rules or properties of limits. And before we get too overwhelmed by these rules, I think they're actually all pretty intuitive. So we really don't need to remember any of these rules if we just get comfortable working with limits. So for instance, let's look at this first formula here. It just tells us that the limit as x goes to a of a constant is still just that constant. And that makes sense, right? Because if we have the limit as x approaches 2 of, let's say, 4, well, what this is saying is the function f of x is always equal to 4. The function is a constant. So that means that the value of the function is going to be 4 everywhere. So when x approaches 2, of course the limit is still just going to be 4. If x approached any number, the limit would still be 4. And the same is true for these others. If I'm taking the limit as x approaches 2 of 3x squared, this rule is telling me that I can just bring the 3 out in front. This is the same thing as saying 3 times the limit as x approaches 2 of x squared, because I have this constant multiple of 3. But of course you know that to evaluate this limit, you can just use substitution and plug x equals 2 into 3x squared. You get 2 squared is 4, 4 times 3 is 12, and the result will be 12. If you pull the 3 out in front, of course you're going to get the same thing. 2 squared is 4, now you've evaluated that whole limit, so the result here is 4 times 3, and you still get 12. So it's just telling us we can pull out this constant multiple. This third rule is telling us that if we have for a function a sum, so let's say we have sine of x minus, let's say, 8x squared, that we can take the limit of each term individually. We can first take the limit of sine of x, then we can take the limit of negative 8x squared. Again, basically just telling us we can do it term by term. And this applies as well if we have a negative sign here, if we have f of x minus g of x like this, then we get the limit of x minus the limit of g of x. Or if we had sine of x plus 8x squared, then we say the limit of sine of x plus the limit of 8x squared. So whether you have a sum or a difference, it works either way. And this is the same kind of rule for the product, for the quotient, for a power function here. An example of this might be if we have a function 3x to the 6th minus 2x, and this is raised to the 4th power. We're taking the limit as x approaches 2. All this is saying is that we can take the limit as x approaches 2 of this inside part first, 3x to the 6th minus 2x, and then raise that entire result to the power of 4, and it's going to be the same thing either way. You can also think about this in words, right? This formula here for the sum or difference, you could say the limit of the sum is equal to the sum of the limits, or the limit of the difference is equal to the difference of the limits. Here for the product formula, we would say the limit of the product is equal to the product of the limits, or the limit of the quotient is equal to the quotient of the limits. That same kind of thing holds for all of these rules, so that's a good way to remember them. One point 6 is all about realizing that you can use algebra to manipulate limits in order to solve them. We see that very often in a few circumstances. One is when we use factoring to solve a limit. So we manipulate this algebraically in order to rewrite the function. What we realize here is that we can factor the numerator into x plus 5 times x minus 5, and then in the denominator, we're still left with x minus 5. And then here, we see that we have a factor of x minus 5 in both the numerator and the denominator. We cancel, and we're left with simply x plus 5. So now we have this limit as x goes to 5 of just x plus 5. We can at this point use substitution, and what we end up with here is 5 plus 5, or 10. If we had originally tried to plug 5 into the original function, we would have gotten 0 in the numerator and 0 in the denominator for an indeterminate form of 0 over 0. But with a little algebraic manipulation through factoring, we can see that the limit is 10. We also see this a lot with conjugate method. So we'll have limits like this. The limit is h goes to 0 of 2 minus root 4 plus h divided by h. If we just plug 0 into this function, we'll end up with the indeterminate form 0 over 0. But we can use algebraic manipulation through conjugate method to find a limit. And remember the conjugate method, we just take the two-term binomial, in this case that's our numerator. We keep the same two terms but change the sign. So instead of 2 minus, we'll do 2 plus. So we have 2 plus, we leave everything else the same, like this, and then we divide by the exact same thing. So 2 plus root 4 plus h, like that. And then we multiply this out, we get 2 times 2, remember we have to FOIL this out, we have to use distribution here, so we get 2 times 2 is 4. Then we get plus 2 times root 4 plus h minus 2 times root 4 plus h. Those two middle terms cancel each other, leaving us with just minus root 4 plus h times root 4 plus h, or minus 4 plus h because the square roots cancel. And then in the denominator, we end up with h, 2 plus root 4 plus h, like this. And then we can see that in our numerator, we get 4 minus 4 to cancel to 0, leaving us with just the negative h in the numerator. So negative h divided by h times 2 plus square root 4 plus h. And now if we've done everything correctly, we should be able to get an h to cancel. We can see that we get the h's to cancel from the numerator and denominator, leaving us with just negative 1 divided by 2 plus square root 4 plus h. And now that we've done the simplification, we can go back to substitution, plugging in h equals 0. When we do, we get 4 plus 0 is 4, square root 4 is 2, 2 plus 2 is 4, and so the result is negative 1/4. So we realized that when we used substitution originally, we got an indeterminate form, but after using conjugate method, we were able to get to a real number answer when we evaluated the limit, and we can see that the limit as h goes to 0 is negative 1/4. And the other kind of limit we see this most commonly is with trig limits. And remember that with trig limits, we're always trying to get our trig function to match some other trig function whose limit we already know. So for instance, with this problem, we already know this limit. This is a formula we should have memorized. The limit x is 0 of sine of x over x equals 1. We know that this limit is true. We're trying to find the value of this limit. But what we have to realize with these trig limit formulas is that we're trying to get these values here to match. We have sine of x divided by x. So the fact that these are both x tells you they need to be the same. In our problem, we have 2x for the argument, but just x in the denominator. So in order to make these match, we want to multiply this denominator by 2 so that we can have 2x in both spots. But of course, if we're going to multiply the denominator by 2, we also need to multiply the numerator by 2. So we multiply the denominator by 2 to get 2x, and then we multiply the numerator by 2 so that we don't change the value of the fraction. But what we can see that we have here now, if we factor out this 2 in the numerator, is that we essentially have 2 multiplied by sine of 2x divided by 2x. And we can see now that this form inside the parentheses matches this format over here. We already know that this limit is equal to 1. So we can say the limit as x goes to 0. Remember, according to our properties of limits, we can pull this 2 out in front of the limit. So this is the same as saying 2 times the limit of x to 0 of sine of 2x divided by 2x. And we can see that we have matching formats, and so we know that this entire limit here is equal to 1. This whole thing is equal to 1. So this just simplifies to 2 times 1, or 2. And so the value of that limit is 2. These are all examples of how we use algebra to manipulate or rewrite the original function in order to be able to evaluate the limit. The key takeaway from topic 1.7 is really just about the order in which we want to try these different procedures for solving limits. So this is a general guideline for the order in which you might want to try some of these limit rules. And the only reason we put them in this order is really because it's kind of easiest to most difficult. Substitution is the easiest method because it allows us to just plug directly into the function and get a value for the limit. So for instance, if we have the limit as x approaches 2 of x squared plus 1, well, we can just use substitution because we're able to plug 2 directly into the function to get 2 squared is 4, 4 plus 1 is 5, and we can say that limit is 5. All we have to do is use substitution. So you just want to quickly think, can I substitute to find my limit? If so, that's going to be your fastest way to be done. If that doesn't work because you get an indeterminate form, something that's undefined, substitution doesn't work for the limit, then you want to quickly think, can I factor it? Because factoring is going to be your next simplest method. And in general, you're usually only going to factor a rational function. So for instance, if we have something like x squared minus 25 divided by x minus 5, and we're taking the limit as x goes to 5. This is a rational function. It is a fraction with polynomials in the numerator and denominator. Something like this should be a dead giveaway for factoring. And in fact, if you see something like this, you should be comfortable knowing that you can actually skip substitution and go straight to factoring, because this is exactly what factoring problems often look like. And if you do try substitution, you'll see right away you get 0 over 0, so you'll go on to this next step. Anyway, so you want to try factoring if you can. If that doesn't work, you want to try conjugate method. Or when you have the limit, often you'll see something like the limit as h approaches 0. You'll see that you have h by itself, either in the numerator or the denominator, and then you might see something like 2 minus the square root of 4 plus h, something like that. We can see right away with substitution we're going to get 0 over 0. This is not factorable, so our next step would be conjugate method. And it's a dead giveaway that this is a conjugate method problem, because whenever you have the sum or difference of two terms, either the numerator or denominator, and one of them's under a root, it's not the only kind of conjugate method problem, but it's a very common kind of conjugate method problem. So that's going to be your next option. And then these ones here, trig limits, again, you wouldn't try this necessarily unless you exhausted these three options, but at the same time, if you're given some kind of trig function, something like the limit as x approaches 0 of, let's say, sine of 2x over x, something like that, you see right away you've got a trig function, so you may skip directly to the trig limits option. And remember, with that method, we're trying to match up our function to some predefined trig functions that we already know the limits of, and we're just trying to do some manipulation there. If all of that fails, substitution, factoring, conjugate method, trig limits, none of those seem like they're good options. And if you use substitution to find that you have an indeterminate form, for example, in all three of these cases, if we use substitution, we get 0 over 0. That's an indeterminate form. If you find that indeterminate form and none of these other methods work, L'Hopital's rule is going to be the next thing you want to try to see if that works. Remember, L'Hopital's rule just tells you to take the derivative of the numerator and the denominator, replacing the original numerator and denominator with their separate derivatives, and keep doing that until you get something that isn't an indeterminate form. And then lastly, squeeze theorem. If none of these things work, you can always consider trying to find a limit with squeeze theorem. That might be an option. And in that case, you obviously want to think about which two functions you can squeeze your function in between if you know the limits of those other two functions. So this gives you a general framework for how to approach these limit problems. Always start here with substitution and work your way down the list. That should hopefully help you move through these problems as quickly as possible, and hopefully give you a basis for how to choose which procedure to use to find a limit. We also really need to be able to find limits using squeeze theorem. Remember that squeeze theorem is most often used with trig functions, and we use it to find limits by squeezing the function in between other known functions. So for instance, with this problem, if we try to use substitution to evaluate the limit, we're approaching 0. We run into trouble right away because we're taking sine of the argument 1 over x. We get 0 in the denominator, and we're immediately in trouble. So we can't use substitution. But because we see that trig function, we realize this might be a good candidate for squeeze theorem. And when you use squeeze theorem, remember, you always want to start with, if you have it, just the trig function by itself, because we know that the function sine of x always waves back and forth between -1 and +1. The lowest value sine of x ever reaches is -1, the highest value it ever reaches is +1, so we know that sine of x is bounded between these two values. It's greater than or equal to -1 and less than or equal to +1, so we can set up this inequality, and that's true. We can also always change the argument. Remember, this is also true for the cosine function. Cosine also waves back and forth between -1 and +1, so we can set that up with the same kind of inequality. And then we can always change the argument of a sine or cosine function. So even though this is sine of 1 over x, changing the argument here from x to 1 over x does not affect this inequality. A sine function of any argument, same thing with cosine, is still going to be bounded between -1 and +1. So we add in that argument. Then, and what we're trying to do is get this middle function to match exactly our original function. So we want to raise this sine function to the base e. So we want to raise this to the base e, raise this to the base e, and raise this to the base e. Realizing that anything we do to any part of the inequality, we have to do throughout the rest of the inequality. So because we wanted to raise this middle part here to the base e, we have to raise the left and right sides to the base e as well. Now we also want to multiply this middle part by x squared to get that x squared in there, which means we're going to have to multiply the whole thing by x squared. So what we get then is x squared e to the -1 less than or equal to x squared e to the sine of 1 over x less than or equal to x squared e to the 1. Now the middle part of the inequality matches the original function, we can apply the limit. And just like everything else, when we apply the limit to the middle part, we have to apply it throughout the entire inequality. So we say the limit as x goes to 0 of x squared e to the -1 must be less than or equal to the limit as x goes to 0 of x squared e to the sine of 1 over x, which has to be less than or equal to the limit as x goes to 0 of x squared e to the first, or we can just write e. Now that we have the middle part resembling exactly our original limit, we can evaluate the limits. Well, remember, we don't know the limit of this middle part yet. We ran into trouble when we did that. However, on the left-hand side, when we substitute x equals 0, we see that we get 0 here for the x squared. 0 times e to the -1 is still 0. So we end up with 0 over here on the left-hand side, less than or equal to the limit we don't know yet, and then x squared e to the sine of 1 over x less than or equal to, and over here same thing, when we substitute x equals 0, we get 0 for the right-hand side. So even though we don't know the value of the limit in the middle of this inequality, we know it has to be greater than or equal to 0, and at the same time, we know it must be less than or equal to 0. Well, a value cannot be both greater than 0 and less than 0 at the same time, which means that the only value this could possibly take on, we've shown, must be 0. So the value of our original limit is 0, and that's how you use squeeze theorem to evaluate a limit. All we're doing in topic 1.9 is realizing that we can connect limit notation in terms of the function and the limit to tables and graphs and be able to switch back and forth between those representations. So as an example here, we can write the limit as x goes to 16 of the function square root of x. We can use substitution to plug 16 in for x, and we can say that this is equal to root 16 or 4. And so we can say that the value of this limit is equal to 4, and we want to be comfortable with this notation. Equally, we want to be able to present this as a table. So if we see here a table of values and we're asked to estimate the limit as x approaches 16, well, we see here in the table that we're getting closer and closer to x equals 16 from both sides, and it looks like the value of the function is getting closer and closer to 4, and so we say that the limit is 4, and we can find that from the table. And we also want to be able to do that in a graph. So if we have instead here a sketch of the function y equals square root x, like we do here, we want to be able to graphically identify this point here at x equals 16, go up to the point where that meets the graph, and then over to the y-axis and see that the value there is 4, and then translate that relationship to say that as x approaches 16, the limit of the function is 4. And we just want to be comfortable switching back and forth between all three of these expressions of the limit, because throughout the AP curriculum, when we take the AP test, we're going to be presented with all different kinds of information, whether it's this notation here, where we find a limit, a table, where we find a limit, or a graph, where we find a limit, and we need to know that they all correspond to each other, that they all mean the same thing, so that we feel comfortable really identifying that the limit of this function as x approaches 16 is 4, regardless of the kind of information we've been given. Here in topic 1.10, we really want to make sure that we can name different types of discontinuities. So I've got here a totally wild graph so that we can get them all into one picture. But let's look at the discontinuities at each of these points on the curve. So at x equals 3, if we come here to x equals 3, we can see that we have a jump discontinuity because there's this big gap here between these two values. There's a big break in the function. And so at x equals 3, the function has a jump discontinuity. At x equals 4, we see that we have the same thing. We have this big break in the value of the graph. And so this is also a jump discontinuity. But at x equals 5, we have this break between the two pieces, but we're approaching this vertical asymptote on both sides, which means that this is an infinite discontinuity. Sometimes call it an infinite discontinuity, sometimes call it an essential discontinuity, but the point is that we're at a vertical asymptote. And remember that it doesn't matter whether we approach positive infinity from one side and negative infinity from the other, or vice versa, or if we approach positive infinity from both sides or negative infinity from both sides. In any of those scenarios, we have an infinite or essential discontinuity because that vertical asymptote is breaking apart the function, it's making it discontinuous at that point. And so if we have a vertical asymptote, we have an infinite essential discontinuity. At x equals 6 here, we just have this single point. And when you see a single open circle like this in the middle of an otherwise continuous curve, that's a point discontinuity, which we also sometimes call a removable discontinuity. That's different here than the open circles at these other points because all these other open circles are endpoints of a section of the graph part of the curve, whereas this open circle is in the middle of an otherwise continuous smooth curve, so it's a point or removable discontinuity, where x equals 3 and x equals 4, we have jump discontinuities. And then just don't get fooled about something here like x equals 7. This is a cusp, it's a sharp elbow in the graph, but that doesn't mean the function is discontinuous. There's actually no discontinuity there at all. The function is continuous at x equals 7. So just remember that in order to find a discontinuity, you really are looking for a break in the graph. Again, most people say such that you would have to lift up your pencil to go and draw the next part. And here we wouldn't have to lift our pencil at all. We'd come along the curve on the left here, and we would just come to this sharp point, and we'd come up to the other side here. We wouldn't have to lift our pencil off of the paper at all to continue drawing that. There's no discontinuity there. In topic 1.11, we're strictly talking about the definition of continuity, which I've written here. And we kind of want to have this definition of continuity memorized, sort of, but the definition is actually pretty technical. And if we just think in terms of discontinuities, like point discontinuities, jump discontinuities, infinite discontinuities, the definition sort of comes out naturally from that. But it's nice to have this in your back pocket because you can always go back to these specific points or these specific requirements of continuity, just in case you're ever unsure. So the definition is that a function f is continuous at any value x equals c, as long as these three things are true. F of c exists, so the value at c is defined, basically. The limit as x goes to c exists. And remember, that's the general limit. So in order for that general limit to exist, the right-hand limit has to exist, the left-hand limit has to exist, and those two have to be equal to one another. If that's the case, then the general limit will exist. So that general limit exists, and the general limit is equal to the actual value of the function. Basically, it's way easier to think about continuity just as, is there any kind of break in the graph or not, where I would have to lift up my pencil if I want to keep drawing it. But nevertheless, we can still think about the sketch of a function. So we have coordinate system like this, and we have some function, which we'll sketch out like this. Basically, what we're saying here is that at x equals c, so we'll call this c here.
Let's go. Okay, why are you busting in my room?
We have to go.
Okay,
Where's the keys?
okay, I'm coming.
Okay.
Yo, get out of my room, bro.
Alton, you can talk, beat your fucking ass. You want me to beat your ass until you beat his ass? Shut the fuck up, shut the fuck up.
the x-axis, y-axis. So when x is c, we're saying the function is continuous if f of c exists. Well, if I come up here to the graph, right about here, I can see that the function does exist at this point. The graph is defined there. There was no break in the graph. There was no hole in the graph at that point, which means f of c exists. So we can go ahead and say that this curve matches that condition. If we were given the function itself instead of a graph, we could plug in the value of c to the function, and if we get back a real number, then we know that the function exists at that point. So then does the limit exist? Well, in this case, if we follow along the function, the left-hand limit coming in here from the side is approaching this point here. The right-hand limit coming in from this side is approaching that same point. So it's looking like the left-hand limit does exist, the right-hand limit does exist, and they're both going to be equal to this same value, this point here. So the general limit does exist at x equals c, and we've met this condition as well. And then those two values have to be equal to each other. And in fact, that's the case. The value of the limit right here is the same as the value of the function. Remember that sometimes we'll have a function that looks like this, and it'll have like point discontinuity here. So we'll have like a point discontinuity like that, and then we'll be given, somewhere else directly above or below that point, some other point that's part of the function. This is the condition where these two things are not equal to each other. In this case, this kind of case here, the limit is going to be this value right here. That's the limit because the left-hand limit coming in from here and the right-hand limit coming in from here, the graph is approaching this point. But the value of the function f of c is up here. So this here is the limit as x approaches c of f of x, whereas this value up here is f of c. And so they're not equal to each other. That's when you violate that last condition. But in a normal case like this, where the limit is equal to the actual value of the function, then the function is continuous at that point, and you have continuity. So it's just helpful, maybe go through an exercise where you show with a point discontinuity, a jump discontinuity, and an infinite discontinuity, which of these criteria for continuity are violated by each type of discontinuity. Topic 1.12 is really simple and quick. The point here is that a function is continuous over an interval if it's continuous at every point in the interval. And that's pretty intuitive. Basically, we can't call something continuous unless it's continuous everywhere. Basically, we can't say that something is continuous everywhere unless it's actually continuous everywhere. And the biggest thing to remember here is just that all of these functions, polynomial, rational power, exponential, log, and trig, are all continuous everywhere in their domains. So your polynomial function is going to be something like a x squared plus 2x plus 1. And of course, these are just very generic examples. This is kind of a polynomial function. Your rational function is going to be a fraction. So let's say we took this polynomial and we divided it by x minus 1. We now have a rational function. A power function is just going to be a simple x squared by itself would be a power function. Exponential functions are going to be anything with e. Same thing, logarithmic functions are going to be anything like a natural log of x. And then trig functions, of course, are sine of x, cosine of x, tangent of x, etc. The other three, but any of your trig functions. In their own domains, they are just naturally continuous everywhere. That does not mean that every real number is included in the domain. For example, the log function, natural log of x, is only defined when x is greater than 0. If you graph it, you'll see that. There's no part of the graph of natural log of x that is on or to the left of the y-axis. It's only defined for x greater than 0. But for x greater than 0, which is its domain, it is continuous everywhere naturally. Same thing with the trig functions. Some of the trig functions have vertical asymptotes in their graph, and so those points of the vertical asymptotes are not included in the domain. But for any values that are included in the domain, these functions are just naturally continuous everywhere. That's the only idea for topic 1.12. In topic 1.13, we're talking about how to remove discontinuities when we have a removable discontinuity in a function. Remember that a removable discontinuity is only a point discontinuity, not a jump discontinuity, not an infinite discontinuity at a vertical asymptote. So we really only have to worry about removing discontinuities in two types of functions. The first is a rational function. And the idea here is that we factor, as we normally would, and we get x plus 5 and x minus 5, and then we have x minus 5 here. So what we see is that we have a removable discontinuity when x is equal to 5, because if we were to plug 5 into the function, then we get 0 in the denominator, which is going to give us that point discontinuity or that removable discontinuity at x equals 5. But if we cancel out this factor, then we're just left with our function as x plus 5. Now we can see that when x is equal to 5, if we substitute that into the function here, we get 5 plus 5, or 10. So we know that if it were not for the discontinuity, the value of the function would be 10 when x is equal to 5. So in order to remove the discontinuity from the rational function, what we do is we redefine it as a piecewise function. So we say f of x is equal to, and then here we need two pieces. The first piece is the original function, so x squared minus 25 divided by x minus 5. And the second piece is this value here that we just found, the value the function would take on if it didn't have a point discontinuity. So that's our second piece. Then we just need to find the interval for each one of these. Well, we're redefining the function as 10 only when x is equal to 5, because that was the value that was originally causing the problem. So we're redefining the function at that problem point, at that point discontinuity. But for all other values, we can still use the original function. So this is just for x not equal to 5, in other words, for everything else. And now, defined this way, the function is continuous because we have plugged the hole, we have removed the discontinuity from this original rational function. And then the second type of problem that we'll most commonly see is when we're already given a piecewise function and we're asked to solve for this value here of k. So it's this value here. We're asked to solve for that value of k that will make this function continuous. So the most important thing to realize here is what I like to call breakpoint of the function, and that is just the point where one interval ends and the other one takes over. And we can see here that that is at 4. Because for everything to the left of 4, everything less than 4, this first piece is defined for the function. But then as soon as we hit 4, if we're at 4 itself or to the right of 4, greater than 4, then the second piece takes over. So x equals 4 is the breakpoint. We need to be able to identify that. The only thing we have to do to solve for this value of k that forces the continuity of this function is just to set the pieces equal to each other. So we say x plus 3 is equal to kx squared, and then from here we need to use the breakpoint value in order to substitute for x. So because the breakpoint is x equals 4, we'll plug 4 in for x. So we'll get 4 plus 3 equals k times 16, because 4 squared is 16. So we get 7 equals 16k. And if we divide both sides by 16, we get k equals 7 over 16. And so this value here, k equals 7 over 16, is the value that will make this piecewise function continuous. And all that means is that at x equals 4, this is the value that forces these two pieces to join together so that there isn't a jump discontinuity between the two pieces. So we've already talked about discontinuities at vertical asymptotes, and here we just kind of want to connect that to the idea of a limit. And basically, all we're saying, first of all, is that for any function, there's going to be a vertical asymptote where the denominator is equal to 0. So let's say, for instance, that we have 1 over cosine of x. Well, the denominator of this is going to be 0 when cosine of x is equal to 0. So cosine x equals 0. We know that this happens periodically, but if we just start with positive values, we know it happens at pi over 2, we know it happens at 3 pi over 2, and then at 5 pi over 2, 7 pi over 2, etc. And so this function f of x is going to have vertical asymptotes at all of these points, continuing on in the positive direction, and then also in the negative direction. So negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and on like that. All of those are going to be vertical asymptotes. Whenever you have a vertical asymptote for a function, and you're interested in thinking about the limit of the function at that vertical asymptote, you know that you can only have a handful of situations. So let's just go ahead and sketch a generic set of xy axes. And here, let's say that we have a vertical asymptote, so we'll just sketch it like this. Keep in mind here first that technically, in order for a limit to be defined, it has to be a real number value, which means that because we're going to have a function, let's say that does something like this, maybe it comes up here, and it comes down here, because this is heading up toward positive infinity, and this is heading down toward negative infinity, the limit at a vertical asymptote is never technically going to exist, because negative infinity and positive infinity aren't real numbers, they're infinite values. However, we often like to name the one-sided limits around a vertical asymptote, and give them values of positive infinity or negative infinity, just so that we can describe what the function is doing around the asymptote. So if we call this here the function g of x, just so that we're not confusing it here with the f of x that we wrote, then basically what we're saying here, let's call the value of the asymptote here x equals 2. What we're saying is that the limit as x approaches 2 of g of x from the negative side, or from the left-hand side, is positive infinity. From the right-hand side, which we would write as limit as x goes to 2 from the positive side over here, or the right-hand side of g of x is equal to, we can see that as we approach from the positive side, we're going down here toward negative infinity, and so we would call those the one-sided limits. This is the left-hand limit, this is the right-hand limit, and so we would define the left-hand limit as infinity and the right-hand limit as negative infinity. Because these two are not equal to each other, the general limit does not exist. So we would just say in general, the limit of the function does not exist at x equals 2. So whenever your graph splits around the asymptote, if one side of the graph goes up and the other side of the graph goes down, your general limit is not going to exist. If both sides go up toward positive infinity, and you have a left-hand limit of positive infinity and a right-hand limit of positive infinity, then the general limit is going to be positive infinity. If both sides of the graph go down toward negative infinity, so the left-hand limit is negative infinity, and that's also the value of the right-hand limit, then we would say the general limit has a value of negative infinity. So in topic 1.14, we were looking at limits around vertical asymptotes. In topic 1.15, we're switching to horizontal asymptotes. They both have to do with infinity, but realize that when we're talking about the previous topic, 1.14 and vertical asymptotes, we're looking at the limit as x approaches some real number value of a function, and we come up with either positive infinity, or we're approaching that real number value, or we come up with negative infinity, or we say that the limit does not exist because around the vertical asymptote, the function heads in two different directions. But the point here is that those infinite values, the infinity or the negative infinity that you see, those are over here on this side of the limit equation. So the limit is equal to some infinite value. In this case, when we have horizontal asymptotes, you see those infinite values show up in the value that x approaches. So we're talking about the end behavior of a function. So we say the limit as x approaches infinity of a function is equal to some real number value c, or the limit as x approaches negative infinity of a function is equal to some real number value. And so the point here is that those infinite values have moved down here under the limit. Those are the values that we're approaching. So this first case here is when we're talking about vertical asymptotes. The second case is when we're talking about horizontal asymptotes. To help us kind of mentally distinguish between these two sets. So when it comes to horizontal asymptotes, really, we're talking about limits that approach infinite values as describing the end behavior of a function. And we say end behavior because we're talking about what the function is doing at the end of its graph. So if we just go ahead and sketch a generic xy coordinate system, something like this, we might have a function that, let's say, it looks like this, and then it comes this way also, and looks like that. So it looks like there's some vertical asymptote here, but there's also a horizontal asymptote along the x-axis. So the end behavior of the function, what the function or the graph is doing at its endpoints over here on the left and over here on the right, is approaching the x-axis, which is the line y equals 0. And so the end behavior of this function is that there's a horizontal asymptote along the x-axis at y equals 0. All we really want to take away from this lesson is we want to know how to figure out where that horizontal asymptote exists, if it exists at all. So to do that, we want to look at a few rational functions. We'll set them up here. We'll say f of x is equal to, let's call this x cubed plus 2 over x squared. We'll say g of x is equal to, let's say this time, x squared plus 2 over x cubed. And then we'll say a third one, we'll call h of x is equal to, and this time we'll say x squared plus 2 over x squared. The idea here with these rational functions is that you always want to look at the leading term in both the numerator and the denominator. And the leading term does not necessarily mean automatically the first term. It means the highest degree term. So for instance, in this f of x function, x cubed plus 2, x cubed is a leading term because it's a higher degree term than the constant 2. So x to the fourth is higher degree than x to the third, x to the third is higher degree than x squared, which is higher than x, which is higher than a constant. So x cubed is higher degree than 2, x cubed is therefore the leading term. Even if we had instead written this numerator as 2 plus x cubed, even though it comes second, would still be a leading term because it's the highest degree. Okay, so we're looking at the highest degree term and comparing it to the highest degree term in the denominator. And it's that degree of those leading terms that we want to look at. So in this case, we have 3 in the numerator here and 2 in the denominator as the degree of our leading terms. So in this case, we would say 3 is greater than 2, or in our case, the numerator is greater than the denominator. We can contrast that with the function g of x here, where we have 2 in the numerator, 3 in the denominator. And in that case, we would say 2 is less than 3, or the numerator is less than the denominator. And here with h of x, we see only other possibility, which is that the degrees are equal to each other. So here we would say 2 is equal to 2, the numerator is equal to the denominator. The relationship between the numerator and denominator is what tells us where our horizontal asymptote exists, if it does. So when the numerator is greater than the denominator, the function has no horizontal asymptote. There is no horizontal asymptote at all. So the end behavior of the function is that it doesn't approach one specific value. It may wave back and forth, it might head up in one direction one way and another direction the other way, but there's no clean horizontal line as a horizontal asymptote. When the numerator is less than the denominator, then the horizontal asymptote is y equals 0. It is always specifically the x-axis, a line y equals 0, like the graph that we saw up here. And when the numerator is equal to the denominator, in order to find the equation of the horizontal asymptote, we always have to pull the ratio of coefficients from the highest degree term. So this one is simple because we have here in the numerator, this is not just x squared, remember this is 1x squared. It's equal to 1x squared, that's just an understood, unwritten 1. And same thing in the denominator here, we have 1x squared. So the ratio of coefficients, we would take 1 divided by 1. The horizontal asymptote of this function is that y equals 1 divided by 1, which of course we can simplify to 1. So y equals 1 is the equation of the horizontal asymptote for h of x. The key takeaway from this topic is just what the intermediate value theorem says that we can show with a function. So let's say that we have a generic set of axes like this, so x and y, and we have some function, so we'll just sketch in a function, we don't know the equation of it, but it looks like this. The idea here is that if we can pick some interval, so we'll say the interval is from here to here, if we can come down here on the left edge of the interval and find the value of the function there, and we see that it looks like it's this point here, and more specifically, if we come over to the y-axis, I don't know what value we're going to get here, but it's going to be some negative value. And then on the other end of this interval that we chose, the right end of the interval, if we can come up to the function here and see that it has a value right here at this point, and more specifically, if we come over to the y-axis, and I don't know exactly what value we get along the y-axis, but we know that it's some positive value. The point here is if we can show that the function has a negative value at one edge of the interval and a positive value at the other edge of the interval, then the intermediate value theorem is simply just telling us that the function must, somewhere inside of that interval, so somewhere in between this left edge of the interval and this right edge of the interval, somewhere in here, the function has to cross the x-axis, assuming, of course, that the function is continuous on this entire interval. So if we say this is a and this is b, the function has to be continuous on the entire interval ab. But assuming that fact, assuming continuity everywhere in the interval a to b, then if we can show a negative value at one edge of the interval and a positive value at the other, and it doesn't matter if it's negative at the left edge of the interval and positive at the right, or negative at the right and positive at the left, either way, if we have opposite signs, the intermediate value theorem is showing us that the graph crosses the x-axis at this point. And really that's just as simple as, given a function f of x, if we do this algebraically, what we say is that, let's say we have a function and we'll just call it x squared plus 2x minus 6, and let's say we want to show that the function has a root on, let's say, the interval 0 to 4. Well, first of all, we know that this function is continuous on 0 to 4 because it's a polynomial function, and polynomial functions are continuous everywhere in their domain, and their domain includes all real numbers, so by definition, this function will certainly be continuous on 0 to 4, so we don't have to worry about that. Then we just plug in each edge of the interval, so we just say f of 0 is going to be 0 plus 0 minus 6, we get a negative 6, and f of 4 is going to be 16 plus 8 minus 6, and that's equal to 18. So what we can show, we usually call this point where the graph crosses the x-axis, we usually call that c. What we can say is that f of 0 is less than c, which is less than f of 4, or in other words, negative 6 less than c less than 18, simply because of the fact that we found a negative value for the left side of the interval and a positive value for the right side of the interval, we know by the intermediate value theorem that the function has a root somewhere inside this interval, that it crosses the x-axis somewhere between 0 and 4, and we call that point x equals c. Okay, so that's everything for Unit 1. You really want to make sure that you know how to, first of all, evaluate limits from functions, from tables, and from graphs, and how to translate those three things to each other. So if you're going to graph, how that might look in a table. If you're going to table, how that might look as a function, etc. You also want to make sure you know how to solve limits using all of the different methods we talked about. So substitution, factoring, conjugate method, squeeze theorem, trigonometric limits. You want to be comfortable with all of those. And then third, you want to be able to talk about continuity, and you want to know how to remove discontinuities when the discontinuity is actually removable, because of course not all discontinuities are removable. And then lastly, you want to be able to handle infinite limits at vertical asymptotes, limits at infinity, which is the end behavior, and horizontal asymptotes, and the intermediate value theorem. Once you're done with the practice questions for Unit 1, go ahead and jump into Unit 2, where we're going to dig into the derivative, its definition, and all the rules that we use to calculate derivatives.
Hey, let me create, wait, hello, hello, okay. So, honestly, that unit was pretty decent, it wasn't too hard. Uh, there's still some time left, so now I think like that whole unit, honestly, like, it was kind of hard to pay attention to because it was like the same concept of limits repeated and had some like really basic things. But now let's do some of the practice. So yeah, I do know some guy honestly. Yeah. Fine. Okay. So left hand limit. Do I graph this? I think it has to be two. So one is two. Oh, I do not like these questions, to be honest. Let's just look at the answer key. Okay. A, if we try substitution, get undefined value. Instead, let's try substituting a value to the left. Okay. That makes sense. Mhm. 47% of the BC exam, so I should not be worried. Now, what do you want to check my grades? Oh, have trippins and lock in. I'm locked in, bro. Trust. Given the limit, which of the following stands? That's to be A, right? Do you? See, bro, to be honest. Let's go back to this. Chat. You know what I feel like? I feel like we should do this all night. I'll pull all night. You're learning AP Calc. Like, we really should. So, I'll see you guys back again at 12 a.m. Probably, probably even later. I don't know. As soon as this birthday party ends that I have to go to, we'll come back and we're going to grind all of Calc. And next June, we're gonna do all of AP Physics C mechanics, and the next one we're gonna do all of AP Physics C electromagnetism. So yeah, but let me quickly, while my screen is off, yeah, I can't let you guys see my plan for AP Physics C, but we're just, what do you have? 323-minute premise? Okay, that is so much. You save this just in case we're gonna use this. Every single AP Physics C mechanics topic covered. Okay, these videos are not too bad though. They're like they range from 4 to like 20 minutes. Does he have like unit reviews? Okay, I'm gonna do more research on what I should do for physics. Like, this actually could. I see another guy has a video where this, oh, this is before they switched up. Let me just keep this guy just in case. This Saints longer, which We got AP Physics stream planned out. I'll quickly get AP Physics C electromagnetism. I don't know, electricity and magnetism. Okay. We'll just save this. Got some good resources. This guy goes to Harris. Yeah, okay. Eight AP Physics C exam released. What the? Yeah. Stream's playing out, but I'm gonna see you guys back again tonight, and we're actually gonna speak on AP Calc. But other than that, peace.